Bismillahirrahmanirrahim. This is a continuation of the previous talk here. Today we're going to talk about the factor theorem, okay? The factor theorem, okay? Now, I'm going to review briefly, again, about what we talked about last time, okay? And last time I gave you a hypothetical polynomial function, okay? And I suggested that in order to graph a polynomial function, it's really helpful to know the end behavior of the polynomial function, okay? And it helps also to know the zeros of a function or the x-intercepts of a function. Now, the zeros of a function, you can call them like S1, S2, S3. Now your book uses K instead of S, but I have to use S for a reason, because I think it makes more sense. Nevertheless, so S4. Now, which I'll explain, because we have done this before. See, A times X minus S1, X minus S2, and we had used S1 and S2 for the x-intercept of a parabola. So it's the same concept applies here. So I have chosen to use S instead of the K that the book uses, okay? Now, so, and then I said, another way of saying this is that a zero is where the f of that input is 0. So f of S2 is going to be 0. And then f of S3 is going to be 0, and f of S4 is going to be 0. In this, for this function, for example, f of S1 is going to be 0, f of S2 is going to be 0, f of S3 is going to be 0, and f of S4 is going to be 0. This is a quality of all the zeros. So zeros is where, when you plug that point number in, you get 0 for the function. Okay. Now, I hope you understood that. And then I said, how we use synthetic substitution? I said, well, if I gave you a function like this, right? And then blah 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 goes over here, and you put a number over here, right? And then you do synthetic substitution, and then you get this to be like remainder here 0. That means f of S1 was 0, right? So S is 0. So we use synthetic substitution to figure out if f of S1 was 0. If that indeed was the case, then we realize that this is a 0, S1 is a 0. That's how we use synthetic substitution. There is a related concept. There's a related concept, okay? And that is what we're going to talk about, the factor theorem today. The related concept is this, okay? If you're given a function f of x equals something like this, okay? F of x is something like this, okay? Let's say we're talking about this function over here. This is f of x, okay? If f of x is a function over here, and if S1, S2, S3, S4 are indeed the zeros of this function, okay? I'm gonna make a wild guess, okay? I'm going to make a super duper wild guess. It's gonna stun you, and then you probably will have to recover from a shock, with smelling salts or something like that. But, I'm just kidding, of course. But, if this is the function, and S1, S2, S3, S4 are indeed the zeros of this function, I bet that this function can be factored. And the factors are going to be x minus S1, x minus S2, x minus S3, times x minus S4, and there might be something else, other quotient here, okay? We'll call that the blah remainder, whatever. They might or might not be, but this function will be able to be factored like this, okay? Now that's the factor. That's the thought process behind the factor theorem, and we'll explore why that is. Let me repeat this again. So if I give you function f of x equals something, okay, and we know that S1, let's just say S2 and S3 are the zeros. If we knew that, okay, somehow magically, if we knew that, or from, I shouldn't say magic, from a work, inside. We knew that, okay? Then we could say, okay, we could say that this function can be factored, and these are going to be the factors of this function. I'm sorry. And these are the factors of this function. Now, this might be the only factors, or there might be some other left over here. Now, why is that? Why can we say that? Okay? Why can we say that? The reason is, okay, this is from the zero product property, right? The reason is, if, for example, okay, if, for example, this right here, let's call that the S4, okay, is the 0, okay, that means f of S4 is 0, right? Okay. Now, that means, okay, if the function was f of x, okay, then x minus s4 was one of the factors and whatever else remaining over here, okay. The only way this could be a 0 is, okay, x minus s4 was a 0, because, right? Now, remember, I'm sorry, okay, remember, f of x is 0, right? So the only way s4 could be a 0, f of x was 0, is this, if it was a factor. The only way it could be a 0 is if it was a factor, because then we would use the zero product property, which says a times b equals 0, if and only if a equals to 0 or b equals to 0. Okay, that's the zero product. So if s4 is a 0, then it's a factor, because then from the zero property we could say x minus s4 equals to 0 or this blah 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 equals to 0. And from this we get x is equal to s4. Do you understand? So it's because of the zero property. And working backwards, you say, if for this to be a 0, for s4 to be a 0, then this must be true, right? Because x must be, right, is 0, then x must be true. Right? And from this, going backwards from the zero property, we can say that it has to be a factor of the function. You follow? Of the function. So it's like going backwards from the zero property. So if you say x is equal to s4, when, right? F of x is 0 starting from this 0 over here. Then if this is the case, then this has to be the case, and this is the case, that has to be a factor. Okay, so that is the factor theorem. Okay, I'm going to state this now. The factor theorem states, okay, for a polynomial f of x, okay, has a factor, okay, x minus s, I'm going to say s, has a factor x minus s, okay, if and only if, that's a biconditional statement, if and only if, okay, f of s is 0. Okay? Now this sounds like a very complicated statement, but saying if f of x is a 0, okay, then this is a factor of the polynomial. And then the other way of saying that is, because this is a biconditional statement, a polynomial f of x has a factor of this if and only if f of s equals to 0. Now this takes a little bit of thinking and looking over this video probably a couple of times too, to go over this. Okay, so now but you have to kind of digest this and understand. So for example, if x minus 3 is a factor of a polynomial, then we know that 3 is a 0 or f of 3 equals 0. Just like if I give you a parabola like this, x equals 2 times x minus 2 and x minus 3, you knew that the s1 was 2 and s2 was 3. In other words, these are the zeros. In other words, f of s1 was 0 and f of s2 was is 0. You knew that already. See? You knew that these are the zeros. Okay? But you didn't know it in this fashion. Okay? So, read this to yourself, say it like, 10 times, in your mind's eye, and understand that a polynomial f of x has a factor of x minus s1 if and only if f of s is 0. The other way of saying that is, if f of s is 0, then x minus s1 is a factor. I kind of prefer that anyway. If a polynomial has, if f of s is equal to 0, then x minus s is a factor. Okay, perhaps it's easier to remember. It's like this: if f of s is 0, then x minus s is a factor of that, is a polynomial. Now, if you understand this, you are ready, inshallah, to go to our third step, and that is to combine these concepts of synthetic substitution and this factor theorem to find the zeros of the function. Until then, as-salatu was-salamu ala rasulillah. Assalamu alaikum.